Hey everybody, Mr. Ranger here, going to talk to you about 3.2 today, vector operations. Last week we talked about vectors, what they are, how you can move them around and add them up or subtract them to show different types of vectors. Today we're going to talk about how we can put vectors together in order to accurately move in 2 dimensions. So in terms of vector operations, this isn't a specific list of saying first you have to do this, second you have to do that. It's more of a general idea of setting things up properly. Alright, in order to set things up properly, we'll start with step 1, and we're going to establish a coordinate system. Alright, we're going to establish a coordinate system. Now, being in chapter 3 and we were talking about two-dimensional motion, a coordinate system is really going to help us kind of figure out how we are moving and in which direction that we are moving. So a simple coordinate system is just like you would see in math, where you have your quadrants. I think it goes 1, 2, 3, then 4, where if we are using directions, you have north, south, east, and west. And we are also going to establish that up is positive and to the right is positive, while down and to the left is also negative. It happens for 2 reasons. One, this helps us describe motion in 2 dimensions. When we're looking at vectors, it helps us describe motion in 2 dimensions, whether it's going up or down or left or right or north, south, east, west, whatever. Alright? It also simplifies motion in 1 dimension. Okay? So it helps simplify the motion in the 1 dimension. If you're going up versus down or left versus right, positive versus negative. Okay? So when we establish this coordinate system, it's going to help us describe our motion in 2 dimensions, and it's going to simplify our motion in just 1 dimension. Alright? Now, while we are looking at vectors, we're going to be adding them up, moving them around, just like in section 1. So with this coordinate system, we can determine resultant magnitudes and direction. Okay, by adding these vectors up, we can determine these resultant magnitude and directions. And there's a couple different ways that we can do this, and it's almost a recap from section 1. Is we're going to use the Pythagorean theorem. Use the Pythagorean theorem to find the magnitude. Okay, so we're going to use the Pythagorean theorem to find the magnitude of the resultant vector. Okay, we're going to use that, and again, you just have a squared plus b squared is equal to c squared. Alright. We are also going to, this could be a little bit new, we are also going to use the tangent function on your calculator. We're going to use the tangent function to find the direction. Okay, so using the Pythagorean theorem, a squared, b squared, and c squared, we can find how long the vector is to make it to the end. Using tangent, we can actually figure out which direction. So now, if we just have a simple triangle where you have an x, you have a y, and then you also have your resultant, right? Inside, you have an angle, and this is a 90-degree right triangle. This down here, this symbol, you've probably seen in geometry or trig or maybe even in some pre-calc stuff. This symbol is theta. Theta. All right? That is the Greek symbol. It means the angle. Okay, so that angle right there is your theta, where x is the direction in your x, y is up and down, and your resultant is the displacement between the two from down here to where you started to where you finished. Now, you've probably seen this more, hopefully, in something that looks like this, where you have different parts or pieces of the same right triangle. If I redraw it here, we're going to have the blue that's going that direction, and the red that's going this direction, where this is, in math, your hypotenuse, this opposite side over here, and meaning that our angle right here, this is your adjacent side of your triangle. Okay? This for sure you've seen in geometry and trig, hopefully, that you have your angle here. This is your adjacent side because it is next to the angle. It's adjacent to the angle. You have your opposite side because this is the opposite side of your angle. And then you have the hypotenuse, the longest length of your triangle. All right? You've probably heard a set of terms, I'm hoping that you've remembered, that's called SOHCAHTOA. All right? SOHCAHTOA is basically how you are finding sine, cosine, and tangent. I'm not going to talk to you about how or what sine, cosine, and tangent is, but we are going to be using those functions on your calculator and in math to figure out the inside parts, the angles of your triangle. So for a quick recap, so that is the sine of an angle is equal to the opposite over the hypotenuse. Ca is the cosine of an angle is equal to the adjacent divided by the hypotenuse. And TOA is the tangent of an angle, which is equal to the opposite over the adjacent. Okay, so we set up here that we're going to use this tangent function to figure out the direction. And this angle represents the direction that this person, object, thing, whatever it is traveling. This vector is traveling. All right, so to find this angle, so to find the angle of direction, use the inverse function, inverse tan function on your calculator. Okay, so so this theta is equal to tan to the minus 1, the opposite over the adjacent. All right, if you do not know where that is, if you have a nice fancy calculator like mine, your inverse or your sine, cosine, and tangent are these functions right here. If you hit the second button and then hit the tangent, you'll have a tan to the minus 1, and then if you put like 15 over 30, it tells you the direction that you would be going if you knew the lengths of the two sides of the triangle. Again, it's not really super important that you know what each function mathematically where it comes from, just how to use it. All right, so we're looking at this angle right here, and using this tangent function we can figure out the direction that it would be going. All right, so that's kind of step 1 and step 2. From here we can also take our vectors and we can break them down into pieces. And to break them into pieces, that's called breaking them down into components. All right, so for part 3 we can resolve vectors into components. All right, in 3.2 it talks about how not only do vectors have a X quality and a Y quality. Since we're talking about two-dimensional motions, they have bits of both, X and Y's, all right? So horizontal and vertical parts of vectors are called components. All right, and we can break these components down into different things and we can find them. All right, so components are projections of a vector along the X and Y axes on a coordinate system. Okay, so these components are a major thing. We could tell how far up something is going and how fast it is going along its two different pieces. So if we again draw a simple coordinate system, and we have a component, or I should say a vector, leaving, and let's just say it's at a 45-degree angle to make it nice. You have an X component that is traveling from side to side, and you also have the Y component that helps this object travel up and down. As we start to get into projectiles for our projectile motion, these components are kind of critical because it shows you how fast an object is traveling and how fast it's traveling up and then eventually back down. All right? So any vector, so the part, kind of the key thing is here is that any vector can be described into two components. All right? Any vector, doesn't matter. Parts of it are going up, parts of it are going down or side to side or whatever. Now you could be asking yourself, but Mr. Ranger, what if it's a flat line? Well, that's pretty simple. You have an X component, which is equal to whatever, let's just say 15. You also have a Y component, which is equal to 0. Same thing could be said of a vector that is going up, where you have a Y that's equal to 15 and an X that's equal to 0. Okay? So just because it's moving at an angle doesn't mean that it's the only thing when it has two components. Some ones that are flat, they still have both, but these are just equal to 0. All right? And the last little bit that we're going to talk about today is that we can also add vectors that are not perpendicular. Okay, so we can add vectors that are not perpendicular. Now, what we're going to do is, since these vectors have components, we can actually add these different components together and add the pieces that are in the same direction together to figure out a resultant vector. All right, so you can find the magnitude and direction of resultant vectors, okay, by adding all of the X and Y components together. Multiple vectors traveling in multiple directions can be added together. If you have, let's just say, a vector that's traveling up to here, and then it decides to travel again further in this direction, we can actually take our axis, x1, and over here x2, and add them together, and you have y1 and y2, and we can add these components together figure out how much further they will go. One thing to note here is that our y2 will already include this. So we're trying to figure out this overall resultant vector. All right? From there, once we've figured out our components, we can use the Pythagorean theorem to find the resultant, and we can use the tangent of theta to find the direction. Okay guys, I hope this helped. Using vector operations is actually pretty simple, especially when you establish your coordinate system. Remember, in most of our projectile motion examples, we're going to use up and to the right as positive and down and to the left as negative. It helps describe our motion in 2 dimensions and simplify this 1D motion. It's easy to find the resultant magnitude and direction by using the Pythagorean theorem on right triangles. Remember that the hypotenuse is the longest piece, the opposite is opposite of the angle, and the adjacent of theta is the one that's closest. We learned a little bit about sine, cosine, and tangent, at least how to calculate each of those, even if you don't know what the heck they are. To find the angle, we can use the inverse tangent, which I showed you on your calculator, and this formula right here. We also talked about vectors have components, parts, pieces, an x component and a y component. They don't always have to be more than 0. They can be 0 on flat lines. And that we can add vectors that are not perpendicular by finding each piece and then adding them together using the Pythagorean theorem to figure out our total resultant vector and using our tangent of our angle to figure out which way that we're going. Hope this helps, guys. Have a good day. See you later.